that it's Jaime Vargas Gonzalez, that it's a PhD student at the University of Hertfordshire. And so this is also a topic that I'm very interested in. So it's a Alma variability to study young stellar objects that show some flares. So it will be the first systematic study of these millimeter flares in protostars. So we can start whenever you are ready, Jaime.
Thank you. Thanks, of course, a lot to the MAYA organizers. And actually, congratulations to all the speakers, because there's a lot of interesting research. Thanks for the introduction. Actually, yes, I will talk about Alma variability study and its relevance in the search for high energy processes in YSOs. I also will briefly describe the wider project and where this is part of. So our interest in radio variability from YSOs is actually to understand high energy processes in protostellar systems. The high energy processes can be traced by X-ray emission and radio emission when it comes from non-thermal radio emission. But protostellar systems actually show both thermal and non-thermal emission. The thermal emission will come from more larger scales in the system from circumstellar disks or at the base of outflows or jets. And then the non-thermal radio emission is more relevant into the smaller scales where we find the complex magnetic field structure that sometimes can be not only for a single star, some more complicated structure in binary system. So the electron population that is gyrating along magnetic field lines in this complex structure will be emitting in centimeter range as gyrosynchrotron emission, or at higher energies into the millimeter range via synchrotron emission. So this is a complement to what a lot of X-ray studies have been done so far. And basically what it's saying is that the radio emission will describe the initial phase of a flare event and all the energy from this electron population. And then we will see the heated plasma, the energy that was injected into the plasma, and the X-ray will tell us about the second part. So I'm interested in the radio emission associated to these processes. And the wider project in the search for variability in this context, we are working towards Orion, that you have seen in several talks, because it's a nice playground. We find a lot of sources in a very small areas. It is ideal for single pointings with VLA, with Alma. So with VLA, we have searched the inner part, also the larger part of Orion. And also with VLVA, we have follow up one of the VLA surveys in the inner part of the ONC. In the Alma area, this orange one is smaller, but it's still, there are several sources even in these few arc minutes there. So we are searching for centimeter and millimeter flares. I will quickly go through the centimeter part of the survey. So basically it consists of 2 VLA observations, one reported by Forbig et al. In 2016, that look in the inner ONC with a single pointing for 30 hours with a resolution of 0.1 arcseconds with the C-band of VLA. 100 of sources detected in that area. 4 years later, a second VLA campaign, and now expanded to almost 20 by 20 arc minutes, showed in red that were reported recently. Also 100 of sources. In this case, the observations were not that long as the 30 hours of the central initial pointing. Now these are 5 hours, but still a large area. So from the first VLA pointing, the idea was to search for strong flares. And this is an example of one source in the sample of more than 500 sources, on where these 30 hours of observations were actually spread into 5 observations. This is a YSO in the sample, and the horizontal line is showing the average flux density from the concatenated 5 epochs observations. So these are 30 hours in different days. And you cannot see if there is a flare if you look into the individual 7-hour data points. If you use the same data but into shorter timescales, into images of 30 minutes intervals, you start to see what is going on in terms of flares. And sometimes their RMS will increase so you don't see anything, but you start to see the flare even if you go to smaller So these strong events are hidden in the data, and the way to look for them is going into the shorter time scales. This 6-minute interval, you can see how this event is evolving, and they just disappear because there is a gap in the observations. Using the similar method, we look in the new VLA data for flares. This time we didn't find a strong flare events, but we anyway found a wide range of variability. So these are examples of the new VLA data, where we find variability by a factor up to a 5 in a few hours. These are light groups of 5 time resolution, and we will call variability factor just the maximum and the minimum in this light curve. And we will see this the same definition for the Alma data I will show later. This VLA data is so sensitive that I just quickly mentioned this. You can also look for proper motions, even with 4 years of difference from faint sources. This is a case of a jet from a massive source. And there is also some non-stellar proper motion that we found in the data, but we can talk this on the Slack probably. In a similar way, we also looked into VLBA data. The good thing with VLBA is that these observations are sensitive to brightness temperature levels quite above the levels of significant from thermal emission. So with the VLBA, the survey was targeting all the sources in the first VLA to see how many of them are now detected as non-thermal sources. From the 550, only 123 showed non-thermal emission in this survey, or were detected in these VLBA observations. The first paper is reported by Forry in last year about the detections and the observations. And there's another paper on the astrometry. The idea here is that there were 4 epochs, 2015, then 2 subsequent days in 2017, and then in 2018, to look for variability. There is also already variability in the looking only at the observations without going into high time resolution yet. So in this, I believe 5 hours observations too, or no longer observations, 6 or 12, up to 12 hours. You can see how strong sources detected in, for example, in the first day in 2017 were not detected in the next day. So you can already see quite large variability in the individual epochs. So you can also look not only the variability in between epochs, but also within the individual ones, going to time resolution of a few minutes. This is an example of a light curve in the 4 epochs for a class 1 YSO, where it shows quite a lot of variability, for example, between the first and the 4th epoch, and then a lot going on in the last 2018 epoch. One particular aspect of this is the high resolution. Apart from that we are detecting non-thermal emission, is also the high resolution, milliarc per second resolution of the data. You can extract the emission of the small maps toward any of the sources, where either you detect the source or you detect anything else. So all the emission will come from the source. You are filtering out all the extended emission. So you can efficiently create light curves, but without having to image the data at a different time resolution. You just take the UV data and extract the flux emission, and you can go down to a few seconds time resolutions for the light curves. So from that experience from the centimetric wavelength, we wanted to look into the millimeter range. As I said in the introduction, flares or non-thermal emission, depending on the energies of the electron populations, can go into gyrosynchrotron emission in the centimetric range or millimetric range at higher energy. As we have seen in previous talks, usually millimeter range in YSOs is used to trace the thermal dust emission from circumstellar disks. But in our case, we are interested in the non-thermal emission and looking at short time scales. So far, there are just a few examples of reported millimeter flares from YSOs. Here is, for example, the GMRA in Orion, observed, it reported by Boer using the BIMA array, 3 millimeter. It increased the flux in a few hours and turned to be the brightest source in Orion during these observations, actually more brighter than the BN source, a very massive source and bright at multi-wavelength observations. Another example We have the B773 tau A and DQ tau, both observed at 3 millimeter, showing flares, extreme flares. The particular thing is of these two systems, these are binary systems, and the nature of these flares seems to be that interacting corona of these binary T Tauri stars. So given the lack of a systematic search of millimetric wavelength, we tried to do the same as we did in the centimeter range. Look for a lot of sources and look at their light curve. So we look at Orion, this time in a smaller area, 3 millimeter continuum images around the VN source, field of view of almost 0.2 parsecs, 8 epochs of 1 hour each within a week observed. Sensitivity is 0.1, 0.3 millijanskis per beam, resolution 0.4 arc seconds. So we detected in the concatenated 8 epochs data. So we combined all the epochs and look for sources. We detected 133 sources shown in red here. We can already see the complexity of the emission in the Orion Nebula. It happens at any whatever wavelength you look at Orion, it's gonna be complex. So we look at the light curve for all these 133 sources, and we actually find variability in short timescales of hours to days in the Alma data. This is just a few examples of between the most variable sources. We see how in the first 4 epochs, it was nothing detected. In the concatenated data, you see the flux density about 0.5 millijanskis. And then in the last 4 epochs, you see how there's a brighter emission. Also some examples of some flare that decreases. And then the last epoch, you don't see, or maybe a quiescent state. All other examples of widespread light curves. You can see how some very faint sources is more complicated to detect when you look into Orion in this complex background. One particular example is this one in the lower right corner, where you detect the source in the concatenated data, but only detect this source in one of the epochs and not in any other. The red data points are only upper limits in all these light curves. So we take 3 sigma of the RMS, and even taking 3 times the sigma, this detection in the 4th epoch is quite bright. So we are going to look into this source in this slide. In the concatenated data, it was detected by a signal with a signal to noise of 11, but in the single 1 hour epoch, it was detected with a significance of signal to noise 22. You can see here in the snapshot, only detected in the 4th epoch. The X-ray properties of this source from the COOP survey indicate this is a deeply embedded source. And apparently from the BLBA data, it seems to be a binary system. So probably this flare can have the same nature of the few examples we saw from B773 tau A, for example. This source happened to be also detected previously reported by Forbrick in 2008 to be flaring in centimeter wavelengths using the VLA. So quite an interesting source. And that seems to be similar to the examples of the few examples of 2 millimeter flares found in the literature. Using the same definition variability factor, taking the maximum and the minimum in the sample, we find a wide range of variability in the millimeter sources, and where the brightest sources seems to not be very variable. We are interested in the largest variability, but we can also ask what happened or what is the level of variability we can look in or we can search for with this kind of method when you use this time sliced imaging. So to find this lower limit, we used Alma simulated observations where we use hundreds of artificial constant sources, and we try to simulate the observations we had from the ONC, but with these constant artificial sources. And we found that because of the constantly changing sensitized beam, you will incur in some spurious variability. This is not a limitation for the Alma itself, but it's just to show that the complexity of the Orion Nebula cluster can have some limitations because of the noisy background. just to finalize, if I have time, just to show the timescales on where this spread variability is found. Basically, we between a few hours and a few days, we find variability up to a factor of 5 at all these timescales, which is still short timescales. This is only a week, basically. But there is not only a trend on where we find a flare only occurring at a few hours. It can happen in light curves that have difference of 7 days. So concluding, there are a lot of points here, but the relevant point is that using the synergy of the new radio facilities to look into the radio time domain of YSOs is quite important. One, the sensitivity helps a lot when you go to short timescales. But the idea is to have the capacity to monitor these sources for a long time and to see how it is the evolution of the flags. So we have searched in the centimeter and the millimeter wavelengths for several sources. Actually, in Orion so far, which is ideal to look for several sources in a small area. And that's it. I'm happy to take any questions.
Thanks a lot, Jaime. So I'm very happy with all this time domain astronomy that it's getting more and more popular. So I'm really happy about that.
Indeed.
So I don't know if Marcella is around to.
Yes,
yeah,
I am.
Do you want to read the questions from
Yes.
the chat? Thank you.
Thanks for the talk. I did not really get which physical process can produce this thermal emission, vary in such short time scale in the millimeter.
Perfect. Yeah. Well, actually, the mechanism for the thermal emission is different from what we are looking for. We're actually looking for non-thermal emission at millimeter wavelengths. So this is different from circumstellar dust emission. So the same process that as described at the beginning for centimeter wavelengths, the magnetic structure in the inner, the electron populations durating along magnetic field lines could incur in magnetic reconnection events. The acceleration of these particles will create non-thermal emission. Depending on the energies involved, lower energies will involve gyrosynchrotron into the centimeter range, but into the millimeter range, it is because of the higher energy electron population, mega electron volts, and those will emit synchrotron emission in the millimeter range. So this can be flaring not only because of a single source. Sometimes there are examples as the case of B773 tau or DQ tau. The interacting corona of the binary system could also create some reconnection events, creating strong flares in the millimeter range.
Okay, so it would be like the extension from the centimeter. So the same effects that happen in the centimeter is you are trying to detect them in the millimeter.
Exactly. The difference would be the energies of the electron populations involved.
But so I think there are no more questions in the chat, so I take the time to do a follow-up on this question. Okay, I also had the question. So essentially what you're seeing with Alma, by default, it would be dust emission, but then when you are seeing a flare, you're seeing that this flare is mainly due to this non-thermal emission from the synchrotron or gyrosynchrotron. So considering that now there are starting to get popular this accretion in the disk and so on, so this thermal variability that we can see in the millimeter, can you really distinguish if it's just an accretion event that it's more associated to change in the thermal variability compared to non-thermal variability? So how can we distinguish this?
That's actually an interesting point also for us, because while we have some knowledge of the variability due to flares, it are typically at short time scales of a few days, could be hours, days, weeks. But accretion event also could create variability in the millimeter range, but typically at longer wavelengths, it could be years, but also could be months. But the limit on what are the time scales relevant for the difference between these two types of variability is actually not quite clear. But definitely non-thermal, it would be at shorter time scales.
Yeah.
But it could be a continuum in that. So yeah, that's actually an interesting point for us. But we are at the moment only looking at the shortest time scales for a strong variability both in the centimetric and millimeter.
I
But yeah,
see.
it's a good point to clarify that millimeter variability can also be found from accretion, but typically on longer time scales.
Okay, yeah, thanks for that. I have two more questions. I will post them on Slack, and if some people have more questions, I invite them to post them there.